Ciao, friends. So right here, just gonna talk about related rates and just kind of like the idea of like what these related rates problems are and and helpful ways to think about them. Because the last video we did implicit differentiation. Related rates is really just the application of implicit differentiation. Um, Pretty much what the related rates problems are is you're going to be given some word problem, like some application problem, um, and it almost always gives you like the geometry of some type of situation. So sometimes like they'll give you equations and it'll be like population type things, but but for a lot of these related rates problems, you need to come up with the equations yourself, and that'll be from the geometric descriptions of the problems. So I'm just gonna scroll down here, go to my little problem bank. So let's look at this first one. So this is one I just wrote. Um, this is like a common one that's used. And so it's describing there's a guy, he's walking towards a wall, he has a certain height, he's going at a certain speed, and there's a spotlight on the ground behind him that's pointing at the wall, and it wants to know how fast is this guy's shadow moving down that wall vertically. And so oftentimes, if you can't immediately think of like, okay, what equation am I going to use? I find the best thing to start these problems off with is to draw a picture. So right here, we know that there's like a little spotlight on the ground. Boom, boom, boom. So this is my little spotlight. And this is 20 meters away from some wall. So this is the wall. And I have some dude who's gonna be here walking. La-di-da. And he is 2 meters tall. And he is walking at a speed of 3 meters per second. And so how we can visualize this is that this light is making this little triangle. It's because the light is on the ground and it's going up on the top of this dude's head. That's where it's gonna cast the shadow on the wall. So this is his shadow. So we can label that some other variable. Let's call that H, and we can label his distance from the wall. Let's call that X. And so that makes this distance right here, that's going to be 20 minus X, because this whole thing needs to be 20. And so so now that we kind of have this visualized here, we can think of, okay, what equations are we going to use to get these rates that we want? So right here, we're given his height, that's 2 meters. And right now we're given that dx by dt is a constant rate of 3 meters per second. Yeah, we know that this final x is going to be 5 meters away from the wall. This is something you need to be careful of. So right now it's good to write down your knowns and unknowns so we can think of what equation to use, but you don't actually sub these numbers in until the end, because this x is varying, right? He's walking towards the wall. His height, though, that's a constant 2 meters, so that's not going to be changing. But his the height of his shadow is changing, and the height or his distance away from the wall, it is changing. So we're not going to sub these numbers in until the end. So that's something that I do want to emphasize here. But anyways, let's just say right now, what is our desire? Our desired is this dH by dt. That's what we want to know. So given that, we know like his speed, we're gonna know how far he is away from the wall, and we're gonna know what his height is. What can we do here to come up with an equation that relates the height of the shadow to these things that we know? So first thing we can do is we can recognize that there are similar triangles right here. So this triangle and this triangle must have that same angle because it's that spotlight on the bottom that's casting his shadow up. So we can use similar triangles, like the properties of similar triangles to come up with these angles. So like right now, if this is going to be some angle theta, we know that tan theta is opposite over adjacent. So it's going to be 2 meters. That's not changing. Divided by, this right here, which is going to be the 20 minus x. But this theta is still the same angle for this larger triangle, which means that tan theta is going to equal this opposite, which is h, divided by this, which is just 20. And so now this is where our equation came from. So really the first step is just kind of breaking down what is the geometry of the problem, and that's how you get the equation that you're going to work with. From here down, this is just going to be an implicit differentiation problem because we have our equation of h, and so now we just want to derive both sides with respect to time, and that'll give us this dH by dt that we want. So it actually looks like we don't really need implicit differentiation for this specific question. We can just like, because h is pretty much on its own already, but we're still going to do that because that's really the technique that you do for like all of them. So right now I'm just going to take the derivative with respect to time of both sides. So remember that, right? Because this x, that's not just a variable, that's also a function of time. This h is a function of time. So remember our implicit differentiation, right? We're gonna look at this. So d by dt, let's look at the left side first. Left hand side. So d by dt of 2 over 20 minus x. So this is going to be a chain rule inside the chain rule, right? So let's first deal with this. So that's some input of x, where x is a function of time, that's in the denominator. So that's like having it to the -1. So we're bringing that negative here to negative, and we're knocking that down. Squared 20 minus x squared, and we're multiplying this by the derivative of the inside. So that's gonna just be, -1 times dx by dt. Remember that one, because x is not what we're taking the derivative of here. We're taking the derivative for time. So this negative is going to cancel out with this negative, and we're going to get dx by dt. And so a really common notation is just putting that dot on top. So the dot means d by dt. So you can either like do it that way whenever you know that the derivative is time. This comes from physics. This is a physics thing. Otherwise, you can just write dx by dt. So you know what you're taking. derivative with respect to. But yeah, so that's it for this side. And then on the right hand side, we just take the derivative of h. So this is just gonna be dh by dt divided by 20. So combining both sides right away, we can just isolate dh by dt. That's nice. dh by dt. That's going to equal 20 times this 2. So that's really going to be 40 times dx by dt divided by 20 minus x squared. So that's nice. We don't even need to calculate what the height of the shadow is to get this. Because right here, this final step now that we're going to do, this last step, is just to sub back in those numbers. So this is why we wait to the end to make sure we get the derivatives correctly. Because that's a mistake that I do see people make is right here, where we kept this this 20, or for example here, so this 20 isn't changing. Like the spotlight is 20 meters from the wall. That's not changing. So we can have this number in our equation. And the rate of change of that is going to be 0. This 2, his height isn't changing. So we can have that 2 there. So really in your equation, don't sub the numbers in unless like you're certain that the thing isn't changing. And then here, this last step, we sub in the rest of the numbers. So we're going to have 40 times dx by dt, which was, what was that? That was times 3 divided by 20 minus 5 squared. So yeah, this is going to be something, I don't know, throw in your calculator. But and then we're gonna check to see what the units are, right? So everything here that we're dealing with was meters, and then yeah, and so we have meters per second here. So this 2 was 2 meters times 20. So this is 40 meters squared, but in this denominator, that's meters squared, so that's going to cancel out. So all we're left with is meters per second. And so like, since this is an application problem, it's a word problem, you need to give like your answer in units and like in a sentence, like therefore his shadow is going down by this many meters per second. And keep in mind what negative signs mean, right? So if we're saying it's decreasing, then like we would say, like, so for example, like if this is, like if we have a positive number and we're saying it is decreasing by this much, or alternatively, we could say it's increasing by the negative number. So keep in mind that in these application problems, that the negatives just kind of indicate directions, right? So that's just going to be dependent on how you defined like what's going up, what's going down, things like that. So yeah, that's really the main thing I wanted to emphasize for these problems is they're gonna give you some description. It's usually just gonna be like a geometry problem. So you can draw a picture. From that picture, you get your equation. From that equation, do your implicit differentiation, rearrange, sub the units in last, and that'll give you your answer. So here's another one, and it's gonna be like really similar strategy. So we have a spherical bubble, you're outside blowing bubbles, that's fun, but it's cold, so it's condensing, the volume's decreasing at a constant rate of this. So we know something, we're given dV by dt that equals, so I guess if we want, we could say negative, right? Like And just like at the end, keep in mind that this negative just means it's decreasing. So negative 4 centimeters cubed per second. And we want to know what is dr by dt at r equals 2 centimeters. So how do we do that? Well, we're given some geometry. So what's, what relates volume of a sphere to its radius? So that's v equals 4/3 pi r cubed. And so that's where we got the equation from. We do our implicit differentiation, do d by dt. So we get dv by dt, which is nice because that was what we're interested in. We don't need to rearrange that. And then so this just becomes 4 pi r squared times dr by dt. Actually, no, the dr by dt is what we're interested in. We know dv by dt. So we'll just rearrange this now. So we have our dv by dt divided by 4 pi r squared. And that equals the thing that we're interested in, our dr by dt. So the very last step is we just sub in these numbers. So this dv by dt, so that's going to be like our negative 4, and then this r is going to be 2. So this is just going to give us negative 1/4 pi, because this is 2. And our units is going to be centimeters per second. And this negative just means it's decreasing. So when it's saying, what is the rate of change, we can say that it's negative, or we can say it is decreasing by this many centimeters per second. And so again, that's really the main idea with related rates. So that last problem, they just kind of gave you the geometry. Sometimes they'll just give you the equation if they say like, oh, this is the model of a population. So it's just we're given some rates and we want to find another rate, and they're usually related somehow geometrically. If you can't think of the equation right away, draw your picture. Once you get that equation, it's just implicit differentiation. Use the yeah, just sub in your numbers at the end, and then you'll get your answer. That's really the gist of it. I really hope that this clarified it. Yeah, it's definitely make sure you're comfortable with implicit differentiation, you're comfortable with the chain rule, and you keep in mind what your variable is. We stress that because sometimes you'll get like these x's, but you're not taking the derivative with respect to x, you're taking the derivative with respect to t. So anytime you do that, you're gonna get like these dx by dt terms. And that's the whole point of these, right? So yeah, just make sure you're feeling comfortable with that. I hope this helped. I hope this clarified. Yeah. All right.